Hello everyone, again this is Suresh. Welcome you to the third session on this fluid dynamics. Before starting today's session, let us recap what we studied in the last session. If you recall, in the last class we started with applications of Bernoulli's equation. I said there are three applications. One is Venturi meter, the second one is Orifice meter, the third one is pitot tube. This Venturi meter is a device used to measure the discharge flowing through a pipe. So, you talk about what is known as a Venturi flume, that is used to measure the discharge in open channels, which you are going to study in the next semester. So, what is the basic principle on which this Venturi meter works? The basic principle on which this Venturi meter works is by reducing the cross sectional area between the two cross sections, a pressure difference is created. So, measuring the pressure difference between these two sections, the discharge through the pipe can be easily determined. This is the basic principle on which this Venturi meter works. Then we also derived an equation, because just now I said Venturi meter is used to measure the discharge. So, if that is the case, what is the discharge equation if I use a Venturi meter in a pipe? So, for that we derived an equation for this discharge through a Venturi meter. Then we studied the limitations, in other words. So, Venturi meter problems, we started with the Venturi meter problems. There I said there are three types of problems. One is when the pipe is horizontal, the second one is pipe is vertical, the third one is pipe is inclined. We started solving couple of simple problems as far as the horizontal pipe is concerned, and if you recall, I start with this vertical pipe problem also. So, then I also said, I promised that I am going to solve couple of more problems, because if you take out your previous question papers, most of the time you are going to see these problems on this Venturi meter. So, that is the reason I am emphasizing more on these problems, so rather than going further on theory. So, with this basics, let us go back to the point where we stopped last class and continue from there on. So, let us start with this problem. If you look at a couple of sentences of this problem, there is no much difference between the problem what I solved in the last class and the present problem. But if you, as you go on reading this problem, at the later stage of this problem, you are going to see there are a couple of complicated issues. Let us see what is this complicated issue and how to solve this problem. Let us read this problem. In a vertical pipe conveying oil of specific gravity 0.8, two pressure gauges have been installed at A and B, where the diameters are 16 centimeter and 8 centimeter respectively. A is 2 meters above B. The pressure gauge readings are shown that the pressure at B is greater than at A by 0.981 Newton per centimeter square. Neglecting all losses, calculate the flow rate. Till this point, absolutely no issues. We solved couple of problems. So, the solutions what I gave for the earlier problems, the same steps you can solve up to this point. Now, what is the complication of this problem? The complication of this problem is the next sentence. If the gauges A and B are replaced by tubes filled with the same fluid and connected to a U-tube containing mercury, calculate the difference of level of mercury in the two limbs of the U-tube. This is the problem. Now, again I repeat, whenever you are solving energy problems and Venturi meter problems, you need to remember three things. One is continuity equation, Bernoulli's equation or the total energy equation, and the discharge equation for this Venturi meter. What is the discharge equation? Actual discharge is equal to coefficient of discharge into A1 A2 into root of 2GH divided by A1 square minus A2 square whole thing under root. This is the formula you need to remember. Now, in addition to this, so another important formula which you need to remember is, remember the basic principle on which this Venturi meter works is, you are creating a pressure difference between the inlet and throat section. That is, P1 by gamma is the pressure head at inlet, P2 by gamma is the pressure head at throat section. So, if I represent this P1 by gamma is equal to H1, small h1, and P2 by gamma at throat section as small h2, then H1 minus H2 will gives me the pressure difference between inlet and throat, that we represented as small h. Now, kindly recall in the last class, so I said there are two cases. What are the cases? One, if the manometric fluid is heavier than the fluid flowing in the pipe. For example, if you talk about a pipe carrying water and the manometric fluid is mercury, so specific gravity of mercury is 13.6, that of water is 1. This is one case. Suppose if it is the reverse, if the specific gravity of the fluid present in the pipe is heavier than the fluid present in the manometer, then you have a different equation, that is H is equal to X into Sm divided by S naught minus 1. This is when the manometric fluid is heavier than the fluid present in the pipe, or so H is equal to X into 1 minus SL divided by S naught. What is this SL? The manometric fluid present in the manometer, and SL is the specific gravity of the fluid flowing in the pipe. Now, if you remember these 5 formulae, I hope that you are going to solve any type of problem as far as this Venturi meter is concerned. Let us, with this background, let us see how to solve this problem. Now, this is a problem. Kindly look into this figure. Okay. So, this is the inlet and this is the throat section. So, inlet has a diameter of 16 centimeter and the throat has a dia of 8 centimeter. Now, let us look into the solution. So, in the last class I said, before start attempting the problem, kindly note down what is given in the problem. Now, in this case, the specific gravity of oil is 0.8. The next thing you need to calculate is what is the density of this oil. So, density of oil is given by, so 0.8 into 1000. So, what is this 1000? So, specific mass density of water, okay, mass density of water into the specific gravity of oil, you are going to get the density of oil, that is 800 kg per meter cube. Now, dia at A, it is 16 centimeter given in the problem, convert that into meters, it is 0.16. Then immediate thing is calculate the value of A, cross sectional area at A. Now, why A? Because if you look at the discharge equation, QA is equal to CD into A1 A2 into root of 2GH divided by A1 square minus A2 square whole thing under root. There in that equation, you need the value of A1, you need the value of A2. What is A1? A1 is the cross sectional area at the inlet section and A2 is the cross sectional area at the throat section. So, calculate the value of A1 knowing the value of dA. So, therefore, this A1 works out to be 0.0201 meter square. Similarly, come to the throat section or section B. Now, dB is 8 centimeter, convert that into meters, then find the area at B. Now, A2 works out to be 0.005 meter square. Now, what is the difference in pressure between section 1 and section 2? That is PA minus PB is 0.981 Newton per meter square. Sir, from where this figure came? So, this is the value given in the problem. Again I repeat, this PB minus PA. Okay. So, this is given in the problem. You must be very careful here. Now, water is flowing or the fluid is flowing from upward to downward. Okay. So, this is the inlet and this is the throat section. So, therefore, the pressure difference in this case is not PA minus PB, it is PB minus PA. Now, this is given in the problem. Now, if you convert this into Newton per meter square, then this becomes 0.981 into 10 power Newton per meter square. Okay. Now, this is the pressure. Now, if at all if I want to convert this in terms of head, pressure head, then you need to divide this by gamma, the specific weight of oil, or rho into G. So, this is 9810. Just now you converted the given value of Newton per centimeter square into Newton per meter square divided by, so at the beginning you calculated the value of mass density, which is 800 into acceleration due to gravity is 9.81. If you simplify this, you are going to get the value of H is equal to 1.25 meters. I hope all these steps are clear. Now, once you know the value of H, then apply the Bernoulli's equation between A and B, taking the reference line passing through B. So, what is this B? Let us go back to this. Now, I take this as a datum line, this B line as a datum line, and I am going to apply the Bernoulli's equation between the section 1 and section 2. Now, if you do that, the first thing you need to do is write general Bernoulli's equation. What is the general Bernoulli's equation for a real fluid? It is P1 by gamma plus V1 square by 2G plus Z1, that is equal to P2 by gamma plus V2 square by 2G plus Z2 plus HL. Never ever forget this value of HL, that is for a real fluid. I said if it is a ideal fluid, the value of HL is equal to 0. Now in this case, I just regroup these terms. What I am going to do is, I push this P2 by gamma to the left hand side, therefore it becomes, so I am going to replace this A1 and A2 by A and B, because in the figure it is a reference A and B, therefore at 1 it is PA by gamma, at 2 it is PB by gamma, plus Z1 I represent it as ZA minus, so Z2 I represent this as ZB. This must be equal to, push this velocity value to the right hand side, you are going to get this VB square by 2G minus VA square divided by 2G. Now, what is the value of ZA and ZB? Now, ZB is a reference axis or reference line, therefore it is 0. Now, remember ZA is at a height of 2 meters. Now, from where I get this value? This value is given in the problem. Therefore, PA by gamma minus PB by gamma plus 2 minus 0, because this is a datum line with respect to which you are going to measure the value of Z2. Therefore, this becomes 0. That must be equal to VB square divided by 2G minus VA square divided by 2G. Remember, in the earlier step, you calculated the value of PB by gamma minus PA by gamma, which is nothing but the value of H, that is 1.25 meter. Now, remember there I said, so water is, oil is flowing from upwards to downwards. It is not PA minus PB, it is PB minus PA, the pressure difference. Now in this case, in this equation, you are looking for PA by gamma minus PB by gamma. That is the reason I put a negative value of minus 1.25. Very, very important. Again, I repeat, the value what we calculated earlier is PB by gamma minus PA by gamma, which works out to be 1.25. But in this term, I am looking for a value of PA by gamma minus PB by gamma. Therefore, this must be equal to minus 1.25 plus this 2 meters. This must be equal to, keep this right hand terms as it is. Okay. If you simplify this, you are going to get 0.75 is equal to this value. Okay. Call this as equation number 1. Okay. Now, applying continuity equation at section 1 and A and B, we get what is continuity equation? Q is equal to Q1 is equal to Q2 is equal to A1 V1 is equal to A2 V2. Now in this case, so 1 is represented as A and 2 is represented as B. Therefore, A of A, V of A is equal to A of B minus V of B. I am looking for this V of B. V of B is equal to A of A divided by into V of A divided by this A of B. Now if you simplify this, whatever the values you have, you are going to get this VB is equal to 4 VA. Okay. So once you get this 4 VA, substitute this value of VB is equal to 4 VA in this equation. If you look at this, so this equation number 1, you have two variables, one is VB, the other one is VA. Now express this VB in terms of VA. Therefore, you are going to get, there is only one variable. So if there is only one variable, this equation can be easily solved, and if you put these values in equation 1, you are going to get this VA is equal to 0.99 meter per second. Look at this 0.75, that is equal to, so VB is 4A, so VB square, therefore it is 16 VA square divided by 2G minus VA square divided by 2G. So 16 minus 1, it is 15 VA square by 2G, therefore VA works out to be 0.99 meter per second. I do hope that so you are clear with these steps. Then, so you know the velocity. Now how to find the rate of flow or the discharge? Discharge is given by again continuity equation AA into VA. Just now you calculated the value of VA and you know the value of cross sectional area at 1 or A. So cross sectional area at A, which you calculated at the beginning of the problem, and the one what you calculated just now VA, if you multiply these two, you are going to get this Q. So Q is equal to, so VA into AA, so you are going to get that discharge in meter cube per second. This is about the first problem, first step of the problem. Now coming to the second step, what the second step says, okay, it says that if the gauges, there are two gauges which you saw in the figure what I presented there, if these two pressure gauges are replaced by a differential manometer, okay, so what is the value of x, it says. So what is this x? The difference between the left limb reading of the manometer and the right limb of the manometer, that is what we call it as x. Now your aim is to find the value of x. So assuming that you are going to replace these two gauges, let us see how to do that. Now look at this, I modified this figure, I removed this gauge and this gauge, I replaced this gauge by a differential manometer. Okay, I connect one end of the manometer to the inlet section, the other end is at the throat section. Now this is the level difference between the left limb and right limb. I call this value as x. Okay, the difference in manometric fluid between the left limb and the right limb, I call this as x. That's what I presented here. Look at this, difference of level of mercury in the U tube. Let x, difference of mercury between the left limb and the right limb. Recall in the last class we gave this equation, H is equal to x into Sm divided by S naught minus 1. In this case you are using mercury as manometric fluid. Remember, the fluid flowing in the Venturi meter is oil, therefore it is 13.6 divided by 0.8 minus 1. Now remember, this is a vertical Venturi meter connected to a vertical pipe, therefore my pressure head is given by P1 by gamma, the pressure head, plus the datum head minus the pressure head at B plus the datum head at B. Now again, if you club this or rearrange this becomes PA by gamma minus PB by gamma plus, so look at this, so this becomes ZA, I think it is ZB, so it's minus here, okay, there is a correction here, please correct this is minus ZB. Remember, PB by gamma minus PA by gamma, which we calculated earlier, is 1.25. Again I am looking for PA by gamma minus PB by gamma, therefore that plus I put at multiplied that by minus, therefore it is minus 1.25, and this difference is 2 meters. Therefore it is minus 1.25 plus 2, it works out to be 0.75 meters. Now consider this equation. Now my H is equal to 0.75, just now you calculated using this equation, knowing the given values, into x into the specific gravity of mercury is 13.6, that of oil is 0.8 minus 1. So if you simplify this, you are going to get 0.75 is equal to 16x, therefore x is equal to 4.687 centimeter. Again I repeat, so the main aim of this second part of the problem is to find what is the level difference of mercury between the left limb and the right limb. So you earlier in the first part you have two pressure gauges, pressure gauge at A, pressure gauge at B. If I remove pressure gauge at A and B, if I replace these pressure gauges by a differential manometer, the question asked is what is the difference in manometric level between the left limb and right limb. Now if you work out this, you are going to get this difference as 4.687 or approximately equal to 5 centimeter. Okay, I hope it is clear. Right. Let us look for a inclined manometer. We started with a horizontal pipe, then a vertical pipe with simple problems. Then we started with a little complicated Venturi meter fitted to a vertical pipe. Now let us talk about an inclined pipe. Let us read this problem. Find the discharge of water flowing through a pipe 30 centimeter diameter placed in an inclined position where a Venturi meter is inserted, having a throat diameter of 15 centimeter. The pressure of water, the difference in pressure between the main and the throat is measured by a liquid of specific gravity 0.6 in an inverted U tube, which gives a reading of 30 centimeter. The loss of head between the main and the throat is 0.2 times the kinetic head of the pipe. Again read the problem once again. It says that find the discharge of water flowing through a pipe 30 centimeter diameter placed in an inclined position where a Venturi meter is inserted, having a throat diameter of 15 centimeter. The difference of pressure between the main and the throat is measured by a liquid of specific gravity 0.6 in an inverted U tube, which gives a reading of 30 centimeter. The loss of head between the main and the throat is 0.2 times the kinetic head of the pipe. Okay, this problem is different from the problems what we solved till now. Let us see how to solve this problem. Okay, let us start with the beginning. So, as I mentioned earlier, kindly note down what is the data given in the problem. So, the data given in the problem is dia at inlet is 30 centimeter. So, either you can keep it in centimeter or convert this into meters. So, D1 is 30 centimeter. So, immediately calculate the value of A1. A1 is equal to 5 d square by 4. Therefore, it works out to be 706.85 centimeter square. Similarly, dia at throat D2 is 15 centimeter given in the problem. Therefore, calculate the value of A2. So, A2 is 176.7 centimeter square. Now, look at this. Reading of differential manometer X is 30 centimeter. So, this is given in the problem. Look at this. So, this inverted U tube which gives a reading of 30 centimeter. The same thing I mentioned here. Reading of differential manometer X is 30 centimeter. Now, this is very important. Difference of pressure head H is given by, I said, if it is a vertical pipe or an inclined pipe, the value of H is given by this formula. Pressure head at inlet plus the datum head minus pressure head at throat plus the datum head at throat. So, P1 by gamma plus Z1 minus P2 by rho g or gamma plus Z2, this is equal to H. This is one equation. The next equation is, remember, so water is flowing in the pipeline, the specific gravity of water is 1, whereas the fluid present in the inverted U tube has a specific gravity of 0.6. Again I repeat, the specific gravity of water is 1 and that of the fluid present in the inverted U tube is 0.6. Now, since the specific gravity of this manometric fluid is less than the fluid flowing in the pipe, so you need to use this formula. Look at this formula, H is equal to X into 1 minus SL divided by S naught. What is this SL? SL is the specific gravity of fluid present in the differential manometer and SO is the fluid flowing in the pipe. In this case, this is 0.6 and this is 1. Okay, I hope it's clear. Now, that's what I mentioned here, where SL is 0.6 and SO is 1. Therefore, my value of H is equal to 30 centimeter into 1 minus 0.6 divided by 1, and this works out to be 12 centimeter of water. Okay. Now, then loss of head is equal to HL is equal to 0.2 times the kinetic head of pipe. Remember, here it is clearly mentioned that the kinetic head of pipe. So, 0.2 times the kinetic head of pipe. Now, in the last class I said when I was talking about the construction of Venturi meter, so the inlet of the Venturi meter is connected to the pipe diameter. Okay. So, that is the reason here look at this kinetic head is given by 0.2 into V1 square divided by 2g, the velocity at the inlet section. Now, applying Bernoulli's equation between section 1 and section 2, we get, so P1 by gamma plus V1 square by 2g plus Z1, that must be equal to P2 by gamma, or you can replace this gamma as rho g, P2 by rho g plus V2 square by 2g plus Z2, pressure energy, kinetic energy, datum energy, plus when you talk about a real fluid, don't forget to put this head loss. This is HL. Now, again rearrange these terms. So, P1 by gamma plus Z1, put a bracket for this, and take this P2 by gamma plus Z2 to the left hand side with a minus sign. Therefore, this becomes P1 by gamma plus Z1 minus P2 by gamma plus Z2 plus V1 square by 2g. Push this term also onto the left hand side minus V2 square by 2g. This must be equal to HL. Now, just now you calculated the value of P1 by gamma plus Z1 minus P2 by gamma plus Z2. That is the value of H. H is equal to 12 centimeter of water. Now, this whole term I am going to replace this by 12. Therefore, you are going to get this 12 plus V1 square by 2G minus V2 square by 2G, that must be equal to, remember, HL is equal to 0.2 times the kinetic head of the pipe. Therefore, it is 0.2 into V1 square by 2G. Now, if you simplify, so this term, so there is a V1 term here, so bring this V1 term to the other side, and some simplification, you are going to get this 12 plus 0.8 V1 square by 2G minus V2 square by 2G is equal to 0. Okay, I hope these steps are clear. Now, at this stage, apply continuity equation. Again, with the discharge flowing at inlet, the same amount of discharge is flowing at throat section also. Therefore, A1 V1 is equal to A2 V2. Now, A1 is equal to A2 by A1 into V2 or A2 V2 divided by A1. If you simplify this, you are going to get, knowing the values, if you simplify this, you are going to get this V1 is equal to V2 by 4. Now, if you just look at this relation or this equation, 12 plus 0.8 V1 square by 2G minus V2 square by 2G. There are two variables, V1 square, V1 and V2. Now, in the next step, here there is a relation between V1 and V2. Therefore, what I am going to do is, in place of V1, I am going to substitute this V2 by 4, or this V2 is equal to 4 V1. If you do that in the above problem and on simplification, you are going to get this V2 is equal to 157.4 centimeter per second. Remember, so what I did here, so I know the relation between V1 and V2. Knowing the relation between V1 and V2, either replace this V1 is equal to V2 by 4 or V2 is equal to 4 V1 in the above equation, and simplifying that equation, you are going to get this in terms of V2 or in terms of V1. So, in this case, this V2 works out to be 157.4 centimeter per second. Once knowing the value of V2, now discharge equation is given by, so A1 V1 is equal to A2 V2. Since I know the value of V2, so I consider this equation A2 V2. Okay, so that's what I did here. Q is equal to A2 V2. A2 I already calculated at the beginning, 176.7, and V2 is 157.4. If you put this and if you simplify this, you are going to get 27,800 centimeter cube per second, or it is 27.8 liters per second. Okay, this is how you are going to calculate when you encounter this type of problem. Okay, I hope it's clear. Now, probably this is the last problem. There are a couple of problems. If you understand this problem, probably you are in a position to solve any type of problem on this Venturi meter. A 30 centimeter by 15 centimeter Venturi meter is provided in a vertical line carrying oil of specific gravity 0.9, the flow being upwards. The difference in elevation of the throat section and the entrance section of the Venturi meter is 30 centimeter. The differential U2 manometer shows a gauge deflection of 25 centimeter. Calculate the discharge of the oil. The second one is the pressure difference between the entrance section and the throat section. Take the coefficient of meter as 0.98 and the specific gravity of mercury as 13.6. So, if you solve the earlier problems, or if you understand the problems what we solved till now, there is no much difficulty in solving this problem. Let us see how to do this problem. Okay, again start with the basics. Diat inlet given, D1 is 30 centimeter. Immediately calculate the value of cross sectional area at inlet section. So, A1 is equal to pi d square by 4. It works out to be 706.85 centimeter square. Diat throat is given 15 centimeter. Therefore, calculate the value of A2. A2 is 176.7 centimeter square. Now, let section 1 represents the inlet and section 2 represents the throat. Okay. Now, if you look at this figure, this is the inlet section, this is the throat section. Now, then Z2 minus Z1 is equal to 30 centimeter. This data is given in the problem. Specific gravity of oil is 0.9, again that is given in the problem. Specific gravity of mercury is 13.6. The differential manometer reading is X is 25 centimeter. So, what you need to do? you need to first find the value of H. What is this H? The pressure difference between the inlet and the throat suction. Again, since it is a vertical pipe and the Venturi meter is fitted to a vertical pipe, so you need to use this formula, P1 by gamma plus Z1 minus P2 by gamma plus Z2. And remember, so in this case the fluid present in the manometer is mercury and the fluid flowing in the pipe is oil having a specific gravity of 0.9. Therefore, you need to apply this formula X into Sm divided by S0 or Sj divided by S0 minus 1. 25 centimeter given in the problem, 13.6 is the specific gravity of mercury, 0.9 is the specific gravity of oil flowing through the pipe minus 1. It works out to be 352.77 centimeter of oil. This is the value of H. Now, discharge or Q of oil is given by, this is the standard equation which we derived in the last class. CD is equal to A1 A2 into root of 2GH divided by A1 square minus A2 square whole thing under root. Now, you know all the values, substitute the values, and if you simplify, you are going to get the value of Q is equal to 148.79 liters per second. Sir, where is this value of CD? The value of CD, if you remember in the last class I said, this CD is called the coefficient of discharge. Coefficient of discharge is also called a hydraulic coefficient. It is defined as the actual discharge divided by the theoretical discharge. If you recall, in the last class I said, when I am talking about a theoretical discharge, that is for a ideal fluid. In case of a ideal fluid, since ideal fluid do not possess viscosity, surface tension, and they cannot be compressed, so in that case, so you don't have any losses. That is the reason the actual discharge is always less than the theoretical discharge. So actual discharge into the coefficient of discharge, actual discharge is equal to the coefficient of discharge into the theoretical velocity. Now this value of CD is less than or equal to 1. Now, for example, if you assume this value of CD is 0.6, then whatever the value of theoretical discharge you are going to get, theoretical discharge into 0.6 will gives you the actual discharge. That is the importance of this CD, very important. I am going to talk more about that when I am talking about this orifice and mouthpiece in the coming classes to come. Right. Now, that is the first part. Come to the second part of the problem. Pressure difference between the entrance and the throat suction. Now, H just now you calculated, it is 352.77. Now, you rearrange this. So, what I am going to do is P by rho G minus P2 by rho G plus Z1 minus Z2 is equal to this value. But what is value of Z1 and Z2 or Z2 minus Z1? Z2 minus Z1 is given as 30 centimeter. Again, this is given in the problem. Okay. Now, what I did in this case, depending on the data given in the problem, I rearrange this equation. That is the only thing I did. I repeat, this Z2 minus Z1 is given in the problem. Okay. Here you clubbed the terms here. So, what I did in the next step is I rearrange these terms in such a way that I am going to get this Z2 minus Z1 is equal to 30 centimeter, which I am going to replace in the next step. If you look at this, remember look at this, this is Z2 minus Z1 is 30 centimeter, but you are looking for Z1 minus Z2. That is the reason in the next step this P1 by rho G minus P2 by rho G minus, so this is plus, since you are looking for Z1 minus Z2, therefore this becomes minus 30 is equal to 352.77. Now, if you simplify this, if you take to the other term, other side, right hand side, this becomes plus, you are going to get 382.77. That is what I presented here, 382.77 centimeter of oil. Now, P1 minus P2, P1 minus P2 is equal to this into rho G. Now, specific gravity of oil is 0.9. Then the mass density of water is 1000 kg per meter cube. Therefore, this rho G is 900 kg per meter cube. Therefore, this P1 by P1 minus P2 works out to be, so it is 3.3795 Newton per centimeter square. Okay. So, only thing is when you look at the problem, don't get panic. Okay, whatever the equations I said at the beginning of this class, kindly remember those equations and start using those equations. You are in a position to solve any type of problem on this Venturi meter. I hope I covered all types of problems on this Venturi meter. Then the next application is orifice meter. Now, orifice meter is a device used for measuring the rate of flow through a pipe. Sir, you mentioned that Venturi meter is also a device used for measuring the rate of flow. Yes, Venturi meter is also used to measure the rate of flow. Orifice meter is also used to measure the rate of flow. If you recall, in the last class I said pitot tube is used to measure the velocity in a pipe or in a channel, whereas this Venturi meter and orifice meter are exclusively used for the measurement of discharge. Okay. Now, what is the difference between Venturi meter and orifice meter? Now, orifice meter is a cheaper device. That's what I put as a second point. It is a cheaper device as compared to Venturi meter. The basic principle on which this orifice meter works is same as that of the Venturi meter. What is the basic principle? Let us repeat that. By reducing the cross-sectional area between two sections, you are going to create a pressure difference. Knowing the pressure difference between these two sections, the discharge through the Venturi meter or the orifice meter can be easily determined. That is the basic principle for both the instruments. Now, what are the components of a Venturi meter? So, Venturi meter consists of three parts: inlet, or it is also called convergent cone, throat section, the middle part, and the last one is outlet or the divergent cone. Whereas the circular orifice meter consists of a circular plate with a circular opening at the center. Okay. Now, this circular opening, what is provided at the center, is called orifice. Okay. So, orifice is an opening provided in the side of the tank or at the bottom of the tank. You are going to study this definition when you are talking about orifices and mouthpieces. Again, I repeat, orifice is an opening provided in the side of the tank or at the bottom of the tank. Now, the diameter of the orifice is generally varies from 0.4 to 0.8 times the pipe diameter. Again, I repeat. Okay. Suppose if the pipe diameter is capital D, the dia of the orifice is 0.4 times the capital D or to 0.8 times the capital D. Now, recall this Venturi meter. I said the inlet section makes an angle of 21 plus or minus 1 degree with the horizontal, and it has a length of 2.7 into capital D minus small d. What is capital D? The dia of the inlet section at the entrance, and D is the throat small d is the throat diameter, and the throat diameter is approximately equal to half the diameter of the pipe, and the length is also equal to the dia of the throat section. Then come to the last part, divergent section. Divergent section, I said it makes an angle of 6 plus or minus 1 degree with the horizontal. Now, if you look at those dimensions, and the dimensions are the specifications of this Venturi meter and this orifice meter. So, orifice meter, the dia or the orifice dia varies from 0.4 to 0.8 times the pipe diameter. Let us see what is the difference. Why Venturi meter is very popular, why orifice meter is not very popular. Okay, as we proceed further and further, you will come to yourself will come to know why orifice meter is the coefficient of discharge for an orifice meter is very less compared to a Venturi meter. Look at this figure. This is a pipe, and the two black spots what you are seeing here is a circular plate inserted in the pipe. Okay, if you see from the sideways, okay, the light green color what you are seeing is a circular plate. At the center, the yellow color what you are seeing is an opening. Again, I repeat, you have two pipes. In between the two pipes, you have a circular plate with a hole. So, you are going to fix this orifice plate to these two pipes. Then the whole system, okay, behaves as a orifice meter. Now, this is the direction of flow. Water comes, strikes this edge, and it flows like that. This is the flow direction, and this is the flow direction. Now, if you introduce a piezometer or a differential manometer between this point 1 and point 2, okay, and if you measure the pressure difference, okay, whatever the value of x you are going to get, knowing the value of x, you can easily determine the value of q. Now let us see how to find the value of q. Again I repeat, this orifice meter consists of a circular plate with a central opening, and this central opening is called the orifice. Now here there is a special term, most of you never encountered this term till now. We call it as what is known as Vena Contracta. I am going to talk about this Vena Contracta more when I am talking about the orifices and mouthpieces. For the time being, you just know there is a Vena Contracta. Okay. So what are the characteristics of Vena Contracta, where Vena Contracta form? So where exactly, whether it is going to form in orifice, whether it is going to form in mouthpiece, all those things we are going to discuss when I am talking about this orifice and mouthpiece. Let us see how to derive an equation for this orifice meter. Now I will just go back to the previous problem. This is section 1 and this is section 2. At section 1, let us define these terms. D1 is the dia at section 1, which is nothing but that pipe diameter. P1 is the pressure at section 1. V1 is the velocity at section 1. A1 is the area at section 1. Similarly, D2, P2, V2 and A2, the corresponding values at section 2. I repeat, D1, P1, V1, A1 are diameter, pressure, velocity, area at section 1. Similarly, D2, P2, V2, A2, the corresponding values at section 2. Now, knowing these values, so apply Bernoulli's equation between section 1 and section 2. So what is Bernoulli's equation? So Bernoulli's equation consists of three types of energies: pressure energy, kinetic energy, potential energy or the datum energy. P1 by gamma plus V1 square by 2g plus Z1, this must be equal to P2 by gamma plus V2 square by 2g plus Z2. Remember, I didn't put this HL here. Assuming that the fluid flowing in this case is an ideal fluid. Remember, we are deriving an equation for the discharge through the Venturi meter. That is the reason I made an assumption that the fluid flowing to the orifice meter is a ideal fluid. That is the reason I didn't put this HL here. Now, this derivation is very simple. So if you look at the derivation of Venturi meter and the derivation of this, most of the steps are almost common. Okay, don't be panic. So if you look at the derivation of this Venturi meter, the same steps if you remember, so deriving the equation for this discharge for a orifice meter is very, very simple. So what I did in this case, P1 by gamma plus Z1 minus P2 by gamma plus Z2. This push this, it was on the other right hand side, bring it to the left hand side. Therefore, you are going to get this P1 by rho g plus Z1 minus P2 by rho g plus Z2. This must be equal to V2 square by 2g minus V1. So V1 on the left hand side, push it to the right hand side, you are going to get this V2 square by 2g minus V1 square by 2g. Now remember, this is my value of H. What is this? This is the pressure head at inlet, pressure head out outlet. Therefore, I am going to replace this, I call it as small h1, this I call it as h2. h1 minus h2 is equal to h. This is equal to V2 square minus V1 square divided by 2g. I want the value of V2. So V2 is equal to, so if you cross multiply this, this becomes 2gh, that must be equal to V2 square minus V1 square. So you are looking for V2, therefore V2 is equal to root of 2gh plus V1 square under root. Now h is the differential head or the pressure difference between section 1 and section 2. Now this is very, very important. For the first time we introduce this. Now remember, section 2 is after the orifice. I repeat, section 2, what I showed in the figure, is after the orifice on the downstream side. Okay, in the direction of flow, first you have the section 1, then you have the orifice split, then you have this section 2. Now at this stage we define this AO. Look at this AO or A0. A0 is the area of the orifice. We define this area of the orifice. I said there is a circular opening at the center, so having a diameter d. if you calculate the area of that opening, that we represented as what is known as AO. Then in the next step, we define what is called coefficient of contraction. So what is this coefficient of contraction? Coefficient of contraction is another coefficient also called hydraulic coefficient. In the last class, if you recall, I said there are three hydraulic coefficients. One is coefficient of discharge, coefficient of contraction, coefficient of velocity. We already defined coefficient of discharge. Coefficient of discharge is defined as actual discharge divided by theoretical discharge. Now come to coefficient of contraction. Coefficient of contraction is defined as, okay, so area of the orifice at suction 2, or area of the jet, area of the jet at suction 2 divided by area of the orifice. I repeat, coefficient of contraction is given by Cc. It is defined as the ratio of area of the jet at suction 2 or Vena Contracta divided by area of the orifice. If you look at that equation what I gave here, so this is the area at Vena Contracta and this is the area of the orifice. Now apply continuity equation. By continuity equation, we know that A1 V1 is equal to A2 V2. Whatever the discharge flowing at A1 or suction 1, the same amount of discharge after flowing to the orifice also passes through this suction 2, A2 V2. From this one, V1 is equal to, so this is, look at this, this is A2 V2 by A1. I repeat, from this continuity equation, V1 is equal to A2 V2 divided by A1. But consider this equation. What is A2? A2 is equal to coefficient of contraction into A0. So what I am going to do is, here in place of V2, I am going to substitute this A0 into Cc. If you do that, you are going to get this V1 is equal to A0 into Cc divided by A1 into V2. Now we derived an equation for this V2. V2 is equal to root of 2gh into, I'll just go back to the previous slide. Look at this, V2 is root of 2gh plus V1 square. Now in place of V1 square, I am going to substitute, so this term, that is A0 into Cc divided by A1 plus V2. So if you substitute this term in place of V1 and if you simplify this V2, you are going to get this V2 is equal to root of 2gh divided by 1 minus A0 square divided by A1 square into Cc square. Believe me, once you put this equation here, it is only a simplification. Okay, need not have to scratch your head too much for this simplification. Only thing is, you need to put this value of V1 here and just start simplifying. You are going to get this V2 is equal to this equation. Now then, how to calculate the discharge? Discharge is given by A2 V2. Why V2? Because just now we calculated the value of V2. You know the value of A2, you know the value of V2. So therefore this V2 is equal to, so Q is equal to this V2 into, I am going to replace this A2 by A0 into Cc. Now put all the values, whatever the values you derived earlier, if you put it and if you simplify this, you are going to get this Cc, you are going to get this equation. Once you get the equation, this equation, you need to find a relation between coefficient of discharge and coefficient of contraction. Now I am going to talk more about this relation in the orifice and mouthpiece problems. Now for this section, if you remember this, that will be more than enough. I repeat, the discharge to the orifice meter is given by A0. What is A0? Area of the orifice plate or orifice or an opening into the coefficient of contraction into root of 2gh divided by 1 minus A0 square divided by A1 square into Cc square, whole thing under root. Again I repeat, I am going to talk about the relation between this coefficient of discharge, coefficient of contraction when I am talking about this orifice and mouthpiece. I hope I am clear. Now the discharge equation finally works out to be Q is equal to Cd into A0 A1 into root of 2gh divided by A1 square minus A0 square under root. What is the difference between the discharge equation of a Venturi meter, the discharge equation of orifice meter? Now there, if you recall, it is A1 A2 area of the inlet section, area of the throat section into root of 2gh divided by area A1 square at inlet, A2 square at throat section, whole thing under root. Now the only thing you need to remember here is, rather than putting A2, you are going to talk about the area of the orifice. So area of the orifice into the area of the jet at section 1 into root of 2gh divided by area of the jet at section 1 and area of the orifice square, whole thing under root. Okay. Now look at this. This is very, very important. The coefficient of discharge of the orifice meter is much smaller than that of the Venturi meter. I said in case of a Venturi meter, there are definite specifications. I said the inlet makes an angle of 21 plus or minus 1 degree. The throat diameter is half the diameter of the pipe. The outlet makes an angle of 6 plus or minus 1 degree with the horizontal. Whereas in case of a orifice, okay, the opening of the orifice varies from 0.4 to 0.8 times the pipe diameter. In case of this orifice meter, okay, if you look at this figure, let us go back to the figure what I gave in the class. Here in this case you have what is known as eddy currents in this case. Okay, so you are going to learn more about this when I am talking about flow through pipes. You have what is known as eddy or pipe losses. So when you don't have standard dimensions here, okay, the losses will be more in case of a orifice, whereas in case of a Venturi meter, these losses are very, very small. That's why the coefficient of discharge of a Venturi meter is much higher compared to a orifice meter. Okay, so that's why most of the time this orifice meter is outdated and this orifice meter is replaced by a Venturi meter. I hope these things are clear. Again I repeat, the coefficient of discharge of a orifice meter is much less compared to that of a Venturi meter. The coefficient of discharge of a Venturi meter is very high. Okay, so you are going to conduct an experiment on Venturi meter. Most of the time the coefficient of discharge of this Venturi meter is more than 0.8, whereas the coefficient of discharge of an orifice, so in our laboratory it will be around 0.4 or 0.42. That is the difference you are going to find. Okay.